We're going to move on to the next presentation by Janine Moses from WOW Laboratories at NASA Johnson Space Center, who will be presenting on heads-up display technology for deep space spacewalks.
Thank you. All right, let me share my screen. Okay, can you all see my PowerPoint?
Yes, we can.
Okay, excellent. Thank you.
It's just in presentation mode.
Oh. Okay, let's see. Let me try that again. Sorry about that. Okay, how about now? Oh. Okay, how about now?
You can see your screen, but it's the PowerPoint screen. You need a full screen, the presentation.
Okay, it does look like it's full screen, but I do have my backup computer here, so I'm gonna switch to that. I'm so sorry.
Okay, at the bottom right corner of the PowerPoint window, there's a little minus sign. There's also a plus sign. Directly to the left, it should be like a poster on an easel looking icon, if you can just click on that.
I do actually have that up right now. Let's see.
Did you choose to screen share your whole desktop, or did you just choose PowerPoint?
I just chose PowerPoint, but I'm gonna open again and try one more time.
Okay.
Sorry about that.
Perfect.
Okay, how about now?
Same problem. Oh, there, it's full screen.
Okay, thank you. So sorry. So hi everyone, my name's Janine Moses. I'm presenting for Dr. Steve Robinson. I'm his graduate student. This is my first oral presentation at a conference. So it's too bad that it's virtual, but I'm happy to be here. I just graduated from UC Davis last summer with my undergrad degree, and I'm currently interning at Johnson Space Center. So I'll be talking about head-up display technology for deep spacewalks, or EVAs as they're called, extravehicular activities. So looking at the context, Dr. Young did a fantastic job describing why we need informatic technology and head-up displays for EVAs, but in general, just to reiterate what she was saying, in the future, mission control will not be as involved in EVAs and in space exploration and surface operations. So that's where head-up displays will aid in EVA ops. And in order to kind of get the advanced head-up display technologies working in an EVA environment, we have to walk before we can run, and we have to crawl before we can walk. So what I'm doing at Johnson Space Center is related to the Reveals grant, which is kind of creating a prototype for this head-up display technology. So the goal of the Reveals grant prototype was basically to create a head-up display that would show that EVA informatics on HUDs can be effective and can enhance situational awareness without adding to the cognitive workload of crew members. So this slide shows some of the things that I presented last year during the poster presentation at the Survey conference. So we have a T-38 flight helmet on the left, that is Dr. Robinson's, and eventually we'd like to show real-time radiation levels to crew members, but right now we were just using light intensity. So we have a photodiode measuring light intensity with a Arduino that processes that data and displays it in a visual format on a COTS display screen on the front. And my fellow researcher, Kaden, and I, we rode a tandem bicycle, also belonging to Dr. Robinson, And there was me wearing the helmet to see that, to double check that we can have some sort of like primary task, in this case, riding a tandem bicycle, and still utilize this head-up display without getting too distracted, essentially. So this just shows a few pictures from the conference last year. We had some people like Dr. Beltran and Greg Schmidt. They both tried on the flight helmet, and they really liked it. So that was really fun to do last year. And now this year, so in fall, excuse me, in October 2019 until the end of this year, I'll be at Johnson Space Center as an intern, and I'm working with the H3PO lab, Human Physiology, Performance, Protection, and Operations lab, and we're essentially creating a helmet-mounted display that we will implement and use on spacesuits in the Neutral Buoyancy Lab, which is the giant swimming pool where astronauts train for EVAs. So this will essentially help, and this display will show EVA-related parameters on the display screen, and this will help inform Reveal's research, and then eventually we'll add in simulated radiation levels to this display. This is an unusual project for NASA because it is low tech, it's low cost, and the timeline is very short. So as I mentioned, I got to JSC in October of last year, and by fall of this year, we will have a fully operational helmet-mounted display that we'll be able to implement and test with astronauts in the Neutral Buoyancy Lab. So you can see the images. The one on the left here shows the swing arm mount that we have, and that this is a 3D printed model from last month, and this will show information that is more readable, that is like readable information. Then the second option we have, and we'll be testing both of these, is the surface mount, which you can see on the right side, and this will just be taking advantage of our ability to pick up on peripheral signals just in our peripheral vision. And the goal here is to show a minimal amount of information that is still effective, like a simple warning light or a symbol or something like that. So because of quarantine and COVID-19, there's been some delays in hardware buildup. So I have a combination here of some hardware that we've developed and some PowerPoint engineering. And this, hopefully over the coming weeks, we'll be able to actually be fully integrated with all the hardware that I'm able to finish building up. So as I mentioned, we have the display screen, and this is potted in a waterproof compound because it will be used in the Neutral Buoyancy Lab. And then it is mounted using the two options, our swing arm or our surface mount options. It's mounted to the visor using suction cups. And then it is hardwired to a Raspberry Pi, which is also kept in a waterproof casing near the right shoulder of the crew member in the primary life support system, or the PLIS. As I mentioned before, this is all commercial off the shelf or 3D printed or spare parts like connectors that the NBL already had. So this is a fairly low cost project. Looking at the software side of things, so as I mentioned, the display screen, it's run from a Raspberry Pi. It will be voice controlled by the astronaut or the suited subject who's testing it. And we have the capability to do a manual override if the voice control fails for whatever reason at the NBL. It is getting its power and Ethernet connectivity via an Ethernet cable and a power over Ethernet adapter for the Raspberry Pi. And then we have a series of display modes that the HMD is capable of showing right now in version 1 of the software. So we have our default welcome screen. We have the phase elapsed time, which is real time, how many hours and minutes have elapsed since the EVA began, or in this case, like EVA training. We also have real time metabolic rate. So my H3PO lab at Johnson Space Center is able to gather the real-time crew member, like their carbon dioxide expiration, and then we can gather that data that is saved in a government cloud and show that on the display screen. In addition, we've got 2 modes to show on the surface mount. So these would turn into symbols with meaning eventually. But right now, we just want to catch the attention of the crew members and essentially see how long it takes them to notice this peripheral signal that's going to be on the side of their visor.
You're at 8 minutes.
Okay, thank you. So before we even get into the neutral buoyancy lab, we want to do some ground testing to make sure that we're able to flesh out all the details from the hardware and software and operations side of the helmet mounted display. So this shows a helmet stand we have with an air circulator so we don't suffocate our test subjects. And then this is a task board with several EVA-like items and tasks on it, like a handrail, several on-orbit replacement units, and different connectors, fluid connectors and electrical connectors that would be typical in an ISS maintenance EVA. So we'll have test subjects egress this helmet stand and then have them do certain activities on this task board while utilizing the helmet mounted display, like checking their phase elapsed time or their simulated metabolic rate in this case. And then at that point, so this shows kind of an overview of the timeline of the project. At that point, once ground testing is complete, we'll be ready to continue with the design review process at the Neutral Buoyancy Lab. And that's when this fall, starting in September, October, we'll be able to actually implement this and test this on crew members at the NBL. So I've been involved with the software and hardware buildup and documentation. Like I mentioned, there were some delays with hardware because of COVID, but I'm able to start going into work again so we can continue that. And then the hope is that at this conference next year, I'll have a picture similar to this that shows the helmet mounted display on the spacesuit with the astronaut utilizing it during their EVA training. And then eventually, because this is for the Reveals grant, eventually we would like to also have simulated radiation data being shown on the HMD as well. Thank you.